Good day everyone! Today, we'll explore combined heat transfer for conduction, convection, and radiation all come into play. These processes rarely act alone in real-world systems, which is why analyzing them together gives us more complete and accurate picture of energy movement. Heat transfer is a fundamental concept in physics and engineering, describing the movement of thermal energy from a hotter region to a cooler region. This energy transfer continues until thermal equilibrium is reached, meaning both regions have the same temperature. There are three primary mechanisms by which this heat transfer occurs. First is conduction, convection, and radiation. Conduction is the transfer of heat through direct contact within a material. It relies on the vibration of atoms and molecules. In a solid, these particles are closely packed, allowing thermal energy to be passed efficiently from one particle to the next. The hotter particle vibrates more vigorously, colliding with the cooler neighbors and transferring some of their kinetic energy. This process continues until the energy is distributed more evenly throughout the material. Convection is a transfer of heat through the movement of fluids, liquids, or gases. This movement is driven by difference in density caused by temperature variation. Hotter fluids are generally less dense and rise, while cooler fluids are denser and sink. This creates a cycle of rising and falling fluid known as convection current, which effectively transports heat. Radiation is the transfer of heat through electromagnetic waves. Unlike conduction and convection, radiation does not require a medium to travel. It can occur through a vacuum. All objects emit thermal radiation, with the amount of radiation emitted depending on the object's temperature. Hotter objects emit more radiation than cooler objects. This radiation is often in the infrared portion of the electromagnetic spectrum. Although very hot objects can emit visible light as well, to better understand and quantify these modes, we use equation. For the formula of conduction, we use Q is equal to negative Ka dT by dx, where Q is the heat transferred. Rate is Watt. K is the thermal conductivity of the material, Watt per meter times Kelvin. A is the cross-sectional area or square meter. dt by dx is the temperature gradient. Here is the formula for convection, where H is the heat transfer coefficient, Watt per square meter times Kelvin. T is the surface temperature, and this is the ambient fluid temperature. Third is radiation. This is the formula for radiation, where this symbol is equal to emissivity, and this symbol is equal to this number, which is constant, and the temperature are in Kelvin. Let's have an example scenario in conduction. Imagine a 0.1 meter thick steel plate with a cross-sectional area of 0.02 square meter. One side is at 100 degrees Celsius and the other side is at 40 degrees Celsius. The thermal conductivity of steel is approximately 50 watt per meter times Kelvin. We want to find the heat transfer rate. Let's understand first the temperature gradient. The formula includes dt by dx, which represents the temperature gradient. It's a change in temperature divided by the change in distance. In our simplified scenario, we can approximate this by dt by dx is equals to T1 minus T2 divided by L, where T1 is equals to 100 degrees Celsius and T2 is equal to 40 degrees Celsius and L is equal to 0.1 meter, or the thickness of the plate. Let's convert to Kelvin. Optional, this is optional but recommended. To convert Celsius to Kelvin, let's add 273.15 to the existing temperature. Temperature 1 will become 373.15 Kelvin, and temperature 2 will be equals to 313.15 Kelvin. Now, calculate the temperature gradient. dt by dx is equal to 373.15 Kelvin minus 313.15 Kelvin divided by 0.1 meter is equal to 600 Kelvin per meter. Let's substitute the values into its original formula. Q is equal to negative 50 watt per meter times Kelvin times 0.02 square meter times 600 Kelvin per meter is equal to negative 600 watt. The negative side indicates heat flow from hot to cold as expected. The rate of heat transfer is 600 watt. Now, let's move on to convection scenario. A flat plate with a surface area of 1.5 square meter is a temperature of 80 degrees Celsius is surrounded by air at 20 degrees Celsius. The convection heat transfer coefficient for this situation is 25 watt per square meter times Kelvin. This is the value is often determined experimentally or from engineering tables depending on the fluid properties and flow conditions. We want to find the heat transfer rate. Now, let's write down all the known values. Let's now convert Celsius into Kelvin. The convection formula can work with either Celsius or Kelvin as long as both this and this use the same scale. However, using Kelvin is best practice in thermodynamics. So our current temperature will become 353.15 Kelvin and 293.15 Kelvin. Let's apply the convection formula. Our Q will be equal to 25 watt per square meter times Kelvin times 1.5 square meter and times 353.15 Kelvin minus 293.15 Kelvin. Now, let's calculate. Q will be equal to 25 watt per square meter times Kelvin times 1.5 square meter times 60 Kelvin is equal to 2250 watt. Let's move on to radiation scenario. A small, perfectly black object with a surface area of 0.01 square meter is at a temperature of 100 degrees Celsius. It's radiating heat into a room at 20 degrees Celsius. We want to find the rate of radioactive heat transfer. First, we write down the known values. We convert temperatures to Kelvin. This is crucial for the radiation formula. Add 273.15 to the Celsius temperature. Our first temperature will be 373.15 Kelvin and the second one will be 293.15 Kelvin. And next, we apply the Stefan-Boltzmann law. Substitute the value into the radiation formula. Step 4. Calculate the temperature term. This is where a calculator is very helpful. Calculate the difference in the temperature raised to the fourth power. Now, let's substitute this result back into the equation. The rate of radioactive heat transfer from the object is approximately at 11.16 watts. You'll find combined heat transfer in power plant condensers, spacecraft thermal shields, building installations, and HVAC systems. Even your laptop manages to stay cold during use.